Dear students, greetings of the day. Kindly let me know how was the audio, how was the video. We'll start. Let us start with this question, a basic question. 11 kV 3-phase star connected synchronous generator has a synchronous impedance of 0.5 plus J4 ohms and is delivering 6 megawatts and 3.5 MVA to the system. Find power factor, load angle and EMF is induced. While solving synchronous machines questions, remember, if you want to calculate load angle, it will come with a package E at an angle delta generally. When you want to calculate power factor angle, I at an angle phi. You will understand when you solve some questions. So in this question it is directly given 6 megawatt is P, 3.5 MVAR is Q. So based on the power triangle phi P Q S, power factor cos phi is first tan phi is Q by P. From this, phi is equal to tan inverse 3.5 by 6. For us to calculate load angle, for that, first let us see P is equal to root 3 VL IL cos phi. P 6 megawatt. So once you calculate the current, So this is the power factor angle, this is delta, load angle. Next question. A 5 kVA 415 volt 3-phase alternator has synchronous impedance of 0.5 plus J4 ohms. Find power factor at maximum regulation, power factor at 0 regulation, percent regulation at 0 power factor lagging, percent regulation at 0 power factor leading. So these are the formulas you have to remember when it comes to power factor at maximum regulation. For maximum regulation, the power factor angle phi should be exactly equal to the impedance angle theta, where theta is tan inverse XS by RA. Power factor at 0 regulation, same logic. Cos theta plus phi is equal to minus ISZS by 2B. These formulas in theory you will get. So these two remember, you have to remember for these conditions. And when you want to find out percent regulation, all you need to find out is E, because V will be always given to you in the question. Voltage rating of the machine will be given to you. If you want to find regulation, you must find E. From that you can find out E minus V by V regulation. So first, theta is tan inverse 4 Off it. So directly substitute the values in the formula. For lagging we take plus, and for leading we take minus. If you take minus, you will get E value Next question, a salient pole alternator has XD 0.8 per unit, XQ 0.6 per unit. It is supplying full load at rated voltage at 0.8 power factor lagging. The power angle, excitation EMF and voltage regulation. So if you want to understand these formulas, kindly revise. In one YouTube session I have given all the details of these formulas, how you got from the phasor diagrams. Kindly check. I think GTQ or CTQ somewhere you will be seeing them. You can check the previous lectures. If you want exactly how these formulas came, I have given for motor as well as for generator for all the possible cases. So these are the formulas you have to use now. So first, if you want to find out, we have to find out psi. From the basic phasor diagram, if this is E, if this is V, if this is IA, angle between V and IA is always power factor angle phi. Angle between E and V is load angle delta. Then this is psi. So psi for lagging condition is phi plus delta. If you want to find out the power angle delta, if you know psi minus phi, you will get delta. Phi will be always given to you in the question. So first substitute. As it is mentioned in per unit, easily you can solve it. So let us take V as 1 per unit rated voltage. It is asked for 0.8 power factor lagging, so sin phi is 0.6 plus IA rated current 1 to 0.6. Excuse 0.6. 1 into 0.8 plus RA0. So when you're solving in per unit, is easy to say. E 1.6068 means E minus V by V, V1 per unit as rated voltage. So you can say regulation has 60.68%. A 550 volt 55 kVA single phase alternator has effective resistance of 0.2 ohms. A field current of 10 amperes produces an armature current of 200 amperes on short circuit test and EMF of 450 volts on open circuit test. Calculate synchronous reactance, voltage regulation at full load 0.8 power factor lagging. It is given in the question, a field current of 10 amperes produces an armature current of 200 amperes on short circuit test. You know SCC characteristic, short circuit test characteristic, a field current of 10 ampere. This much field current is producing a short circuit current of 200 amperes. Similarly, the same field current is producing 450 volts on open circuit. Same field current is producing 450 volts on open circuit. So from OCC what we get is, what is the voltage induced in the armature for a given field current? From SCC what we get is, what is the current flowing in the armature on short circuit for a particular field current. So ZS is V by I, as you know. What is that V is? VOC by IISC for same field current. Actually we take for IISC rated, but according to question, as the data you got is 200 amperes, for that current we can calculate. Means in the armature for a particular excitation, what is the current, what is the voltage? That voltage by current ratio will give you the impedance. That is, as it is single phase, simple 450, it is per phase value only by 200 for same field current. The value is 2.25 ohms. This is synchronous impedance. So as RA is mentioned, you can calculate XS as root 2.25 square minus RA is 0.2. Value is 2.24 ohms. So once you know RA value, once you know XS value, you can calculate voltage regulation by substituting in the formula. V cos phi at 0.8 plus IA RA From this you can calculate IA. Simple. IA is 55 kVA by 550. That's the rated current into RA 0.2 square plus there is no root 3 in this question because it is already mentioned single phase alternator. If it is a 3-phase alternator, check whether it is star or delta. Based on that, you have to put root 3, but not required here. So once you know E value, you already know V value. So 720.08 minus 550 by 550 will give you 30.9% regulation. Actually, synchronous impedance must be calculated at rated current. Actually, IISc rated, the current or the field current who produce IISc rated, exactly what it produced the voltage in open circuit, that you have to coordinate. But according to question, you have no scope. You have to take the data what is given to you and accordingly you have to take it. Almost in this zone, synchronous impedance is almost the same value, almost, because almost OCC and SCC will be linear in this zone. But in this zone, it may slightly decrease because of saturation. An alternator has excess 0.8 per unit connected to infinite bus at rated voltage. Excitation EMF is adjusted to 1.3 per unit. Alternator delivers an output of 0.5 per unit. Neglect all losses. Find load angle, armature current, power factor at maximum output, reactive power at maximum power output. So it is given already, it is delivering a power 0.5 per unit. So P is equal to EV by X sine delta equal to 0.5 and calculate delta. So now you got a power angle for this particular power output. Then if you want to calculate the armature current, IA is equal to E at an angle delta minus V by ZS at an angle theta. It is mentioned E is 1.3, delta 17.92, V you can take 1 per unit and J XS is 0.8 per unit. This is the armature current and the power factor, cos 30.54 lagging. And what you are asked is power factor at maximum output condition. Because only excess is mentioned, you can take delta is equal to 90 for maximum power output condition, right? So IA for maximum power output condition is 1.3 at an angle 90. So whenever you calculate IA, you will get IA at an angle phi. As you know, when alternator delivers maximum power output, the power factor will be leading in nature. That positive sign is communicating that. Power factor is. Next in the question, reactive power is asked. Formula. Reactive power at maximum power output condition. Maximum power output condition delta 90. So V by X is E cos delta minus V. If you substitute, you will get minus 1.25 per unit. Minus is communicating you that the generator is not supplying reactive power but it is absorbing. You already know from the theory that when the generator is operating at maximum power output condition, it will absorb the reactive power and operate at a leading power factor. That's the logic. Lagging power factor means supplying reactive power, leading means absorbing. Next question. A three-phase star connected alternator with RA 0.4 ohm, excess 6 ohms per phase delivers 600 amperes at a power factor 0.8 lagging to a 20 kV bus bar. If the steam input is unchanged, find the % change in induced EMF to raise the power factor to unity. So first, this is the induced EMF in the alternator. It was given in the question, steam input is unchanged, means the active power P remains constant. So if you take P is equal to V IA cos phi, two cases, as V is always a constant value, IA1 cos phi 1 is equal to IA2 cos phi 2. Cos phi 2 is unity. According to question, it is given, find the percent change in induced EMF to raise the power factor to unity. So you have to find IA2 for a power factor unity. First power factor is 0.8 and IA1 value is 600. So this is the new current for unity power factor. For this new current, you can again find out. New induced EMF E is equal to V plus new current at new power factor unity 480 at an angle 0 . If you solve this, you will get new E value. I have just quoted this P is equal to V I cos phi. In general, what we need is I cos phi expression. For 3 phase, you know root 3 VL I cos phi or 3 V phase I phase cos phi. Finally, this is the expression what we wanted for this question. So this is the new induced EMF. Why we are calculating induced EMFs, two induced EMFs. First, the induced EMFs when the power factor and when the current is 600. Next, when the power factor is unity, what is the armature current? So these two induced EMFs, why we are tracking is, the reason is it was given change in the induced EMF to raise the power factor to unity. So first E is 14164.4, next E is 1206. So take percentage change So this is the initial induced voltage and this is the final induced voltage. With respect to that, you have to find the change. So actually it is reduced by 14.66%. A 20 MVA 3-phase star connect alternator with an impedance of 5 ohms and a resistance of 0.5 ohms is operating in parallel with constant voltage 11 kV bus bars. If its field current is adjusted to give an excitation voltage of 12 kV, then maximum power generated. Direct formula, as you know. So if RA is mentioned in the question, as you know, cos theta is RA by ZS, it becomes V square into RA by ZS square. And maximum power is generated when delta is equal to theta. So this factor becomes 1. EV by ZS minus V square RA by ZS square. If everything is in per phase into 3 for 3 phase. A 50 kilowatt, 440 volt, 50 hertz star connected synchronous generator with a per phase impedance of 0.8 plus j 4.5 ohms is working with rated terminal voltage. It is required to supply a constant power of 25 kilowatt to the bus bar. Estimate the minimum excitation EMF and find the corresponding stator current. Minimum excitation EMF for constant power concept. This is the This is the basic power equation, as you know. In this equation, according to the question, this is already given 25 megawatt or 25 kilowatt over bus bar, constant. This is also constant. V, bus bar voltage constant, Zs constant, cos theta, impedance angle constant. EV by Zs cos theta minus delta. In that, V is constant, obviously, Zs is constant. Then what is remaining? If V is constant, Zs is constant, P is constant, this factor is constant, then E cos theta minus delta must be constant according to the context of this question. Right? Then, if E cos theta minus delta is constant, as question implies, minimum excitation voltage, minimum excitation EMF. So, when you say E is minimum, then cos theta minus delta should be maximum. In order to make that factor constant, if E is minimum, cos theta minus delta should be maximum, right? Then, when cos theta minus delta is maximum, if theta is equal to delta again, or delta is equal to theta. Therefore, for this question, for minimum excitation EMF, theta is equal to delta or delta is equal to theta. Will come back. So, what is theta means? Theta is equal to tan inverse 4.5 by 0.8. So, from this, P is 25 into 10 cube is equal to, if all are per phase values, E, V, you have to multiply into 3 for 3 phases. 3 into E value. E minimum, because we are talking per phase, by root 3 into V value, 440 by root 3 by Z is 0.8 plus J 4.5, 4.57 minus V square by Z is, V is 440 by root 3 square by 4.57. Cos 79.92. This only. 25 into 10 cube is equal to EV by Zs cos theta minus delta minus this concept. And you know, here we are talking for E minimum. E minimum, that's the reason why here it became delta is equal to theta, so cos term is vanished. So from this we can calculate E minimum. So remember, this is a line value. This is a line value. That's why we kept by root 3. Hope you understood now. Now, yeah. Corresponding stator current is also asked. So IA is equal to E minus V by Zs. So E is delta 79.92 minus V 440 by root 3 at an angle 0 by Zs 4.57 at an angle 79.92. This is equal to 63.8 at an angle 59 degree. Next, a 3.3 MVA 3-phase synchronous generator rated at 6.6 kV has 32 poles. Its direct and quadrature axis synchronous reactances are 9.6 and 6 ohms respectively. Neglecting Ra, find the regulation and the excitation EMF needed to maintain 6.6 kV at the terminals when supplying a load of 2.5 megawatt at 0.8 power factor lagging. What maximum power can the generator supply at the rated terminal voltage if the field becomes open circuited? If the field becomes open circuited means excitation voltage is 0, E is 0. When E is 0, you know in a synchronous machine which is salient pole type, there are two powers, two terms in the power equation. One is EV by XS sin delta, other one is V square by 2 XD minus XQ by XD XQ sin 2 delta. One is excitation power, other one is reluctance power. If excitation is made 0, excitation power will be 0. Still, there will be some reluctance power. That formula we have to use, V square by 2 XT minus XQ by XT XQ sin 2 delta. And what is asked here? Maximum power. So, sin 2 delta when it is maximum means, or reluctance power when it is maximum means when delta is 45. So, first we have to find out right from the power factor angle that is given already, 36.86. So, the formulas you have to bring back. The first formula what we'll use is tan psi V sin phi plus Ia xq by V cos phi plus Ia Ra. So, what is V here? 6.6 kV. So, 6.6 kV by root 3. So after finding delta, by directly substituting in the formula, we can calculate E. Once you know E, already in the question V will be mentioned if you want to find out regulation. So V is given 6.6 kV, you can find out the regulation now. And the last part of the question is maximum power that the generator can supply at rated terminal voltage if the field becomes open circuited. Reluctance power you have to calculate. It is asked maximum. Maximum reluctance power happens for delta 45. So sine becomes, this is 1. So 3 V square by 2. When excitation is made 0, this is the maximum power. A synchronous motor running at no load with rated voltage and frequency. It is excited to have an induced voltage of 125%. Z is 1 plus J 20%. Calculate the stator current. This is perfect. It is given synchronous motor running at no load. When there is no load, the power output is 0. So substitute the data given in the question. From that you can find delta. Definitely at no load delta is near to 0, as you know, you will get that number. So this is equal to E. it is mentioned, it is excited to have an induced voltage of 125%, 1.25. Let V be 1 per unit and E is 1.25. So 0.01 plus J 0.2 will get 0.2002 cos impedance angle from this 87.13 minus delta minus 1.25 square, ZS is 0.2002 cos 87.13. By solving this equation, you can get delta. Because this is a motor, I is equal to V minus E by ZS minus delta, because it's a motor. This is equal to 1 minus 1.25 This is for motor, expression is for motor. This formula is basically P is equal to, for three phases, EV by xt sine delta plus V square by 2 1 by x cube minus 1 by xt sine 2 delta. This is the power equation for a salient pole alternator. For cylindrical rotor, simply EV by xs sine delta. There is no xt, there is no xq. xq is equal to xt is equal to xs there. Think like this. xq is equal to xd is equal to xs. If you put it, this term becomes 0. If xd is equal to xq, this term will be 0, right? Only this power will be existing for a cylindrical rotor. For a salient pole rotor, this plus this is called reluctance power. It doesn't depend on excitation. That's why in this question, when you are asked, when excitation is made 0, what is the power? Then this power is 0 obviously, but this power will be there because of this factor. Now, to solve this question, first you have to understand the power stages of synchronous motor. For example, if you give some power input to a synchronous motor like root 3 Vi cos phi, 3-phase, out of this power input, some power will be lost first in the stator only because of the copper losses within the stator winding. So, the first armature copper loss. Power input minus armature copper loss is the power output actually, but that is not ultimate output of the power across the shaft. That is like power developed in the armature or in the motor. Power developed in the motor can also be called as gross power developed or mechanical power developed, like that. So, power developed. This power developed is not exactly the power output. Between power output or shaft output or simply output, between this and this, there is another loss coming into picture. That's a combination of many. Number one, as the rotor is rotating, a rotor will experience friction and windage losses, as well as when the flux is rotating, this flux will cut the core and produce iron losses in the core loss. So, core, friction and windage losses, commonly called as rotational losses. Core plus friction and windage loss. There is another loss called as stray loss, which we generally ignore, which is a very small value. That is because of some leakage fluxes, linking, producing some eddy currents, those kind of things. We generally totally ignore it. If you are given some stray losses, some number, tweak it, plus stray losses also. And there is one more point called excitation loss. Excitation loss, I am not mentioning here, I am not putting here, but next I have planned one question. In that question, to find out the overall or commercial efficiency of the motor, how we take excitation loss, I will show you. Generally, excitation loss will not be taken in this particular stage. Reason is simple. In a synchronous machine, when you think about excitation is separate. There is a separate source who is taking care of excitation system. So, it is not the power developed in the armature is supplying the losses and the remaining is coming out. It is not like that. That is why excitation loss, if it is mentioned, how to deal, I will show you in the next questions, coming questions. Now, I am not mentioning any excitation loss. Core, friction and windage. If stray losses is given, plus stray losses also you can take, generally they are ignored. So, this is commonly called as rotational loss. Now, this question carries like this. A synchronous motor is tested by driving by another motor. There is a motor who is coupled to another motor and that motor is driving this motor. First, what is given is, when the excitation is not switched on, there is no excitation in the motor. If the excitation is not there, if the other motor is rotating this motor, there is no induced voltage, there is no armature current. There is no armature current means there is no armature losses. If there is no excitation, there is no iron loss also, you know that. So, this motor who is rotating our given motor should rotate only against friction and windage losses, nothing else. So, as output is 0, the input is nothing but loss, basic equation. So, therefore, the motor who is rotating the given motor, if it takes some input, that input as output is 0 is only to supply losses in that particular motor, because input is equal to output plus losses. First case, excitation is equal to 0. Excitation is not switched on. So, core loss will be 0, no doubt. there is no armature copper loss, no armature current. So it is only rotating against friction and windage loss. So the input taken by the motor, because output is 0, is nothing but losses. Which losses means friction and windage loss. So 800 watts in this question must be taken as friction and windage loss. Once all of you read this question carefully. First read the question carefully, because I have made the font size bigger, I am not reading it. It was given already. Neglect the losses in the driving motor. So don't consider losses in the driving motor. That's why all the input what it is taking is coming as output, and that output is the input of the driving motor. Think like that, input of that motor which is it driving, right? So for that motor, as excitation is 0 and the motor is not rotating, it is being rotated, it's not giving any output. The only loss happening at that first point is friction and windage loss, right? Second case, let us go. When the armature is short circuited and rated armature current is passing through it. Now go back to SCC concept. When the armature is short circuited, you don't need to apply high excitation, because it is already on short circuit. There is no requirement of high excitations. A small voltage is enough to ensure rated current in the armature, because it is on short circuit. Logic you know. So when excitation is less, you can ignore core losses again, because core losses depends on flux, flux depends on excitation, and excitation is very small value, because the alternate is on short circuit, just rated current is passing, you can ignore core losses. One point. Second point is, when the armature is short circuited and the rated armature current is passing. When rated armature current is passing, the armature copper losses will be definitely rated, right? Now remember, armature has a current means rotor is definitely rotating. When the rotor is rotating, when the core losses are 0 because excitation is 0, you can't ignore friction and windage loss, because the rotor is being rotated against this friction, air friction and bearing friction. Therefore, two losses you have to consider in this particular case. One is armature copper loss, other one is friction and windage loss. As excitation is very low, ignore iron losses or core losses. Therefore, the input taken by the driving motor or the output of the driving motor, because you are neglecting losses in the driving motor, that's the context of this question. So all that input taken as output is 0 is loss simply. So what is the loss means? Armature copper loss plus friction and windage losses. So second case, armature copper loss plus friction and windage loss is equal to 2500. Then what is armature copper loss? Read this. Neglect the losses in the driving motor. So you got armature copper loss, which is for rated current. Remember that this is for rated current because rated current is clearly mentioned in the question. Why I am focusing rated current means you are not asked for rated efficiency for rated load condition, half load, that's why. Next, third case is also there. On open circuiting the armature with the rated excitation. Open circuiting the armature with the rated excitation. Open circuit, what will find? Core loss, iron loss, like that, link. Short circuit test, copper loss, like that. Some concepts are matching. So open circuiting the armature with rated excitation. Because the excitation is rated, flux is rated, the iron losses will be definitely rated in the machine. That's okay. The second thing is, it is open circuited. So there is no armature copper loss. But one thing, it is being rotated now. It is being rotated. So it is being rotated means there will be rotational loss, basically that is iron, friction, windage. So watts. Therefore, iron loss or core loss is equal to 1800 minus friction windage is already 800. So now finally you got the core loss of the motor is 1000, friction and windage loss of this motor is 800, and the armature copper loss for full load or rated load is 1700. Question is not for full load. It is not asked to find the efficiency for full load. If you read, you have to find out efficiency for 50% load only. Therefore, 50 kilowatt synchronous motor operating for 50% load means 50% output means 25 kilowatt. So efficiency at 50% load is 25,000 by 25,000 plus losses. List. Number 1, core loss, which is constant obviously. What is the core loss? 1000 watts plus armature copper loss. Rated armature copper loss is 1700, but now for half load, so 1700 by 4. Plus friction and windage 800. Into 100, output by output plus losses. I'm moving on to the next question. A three-phase alternator has 72 stator slots. The stator slots are short pitched by 2 slots. If the pitch factor is 0.9659, then number of poles present in the alternator are. It is short pitched by 2 slots. Let us say slot angle as alpha. You can take alpha or beta or gamma or theta, anything. I am taking alpha, slot angle. The formula for slot angle is alpha is equal to 180 degree by number of slots per pole. Because you want to calculate number of poles in this question, from that formula you will get easily. You know, in the entire machine per pole 180 electrical degrees. So per pole how many slots are there? Each slot will be taking that particular angle called slot angle. The phase displacement contributed by each slot. That's the formula. So the stator slots are short pitched by 2 slots means short pitched angle beta is equal to 2 alpha. Because it is short pitched by 2 slots, the total chording angle is 2 into alpha, right? Then pitch factor, you know already, Kp is cos beta by 2. Then Kp 0.9659 cos beta by 2, beta value is therefore alpha value is 15. Next question. In the next question it is given, the flux per pole in a synchronous motor with the field circuit on and the stator disconnected from the supply is found to be 25 milliweber. This is the flux when field circuit is on and the stator is disconnected from the supply. When the stator is connected to the rated supply with the field excitation unchanged, flux per pole in the machine is found to be 20 milliweber. So with the presence of stator flux, 25 milliweber became 20 milliweber, right? Which means certainly there is demagnetization happening in the synchronous motor. So when flux initially 25 milliweber with stator connected to supply with stator flux, when phi2 became 20 milliweber, there is demagnetization happening. It is certain. Now read the options. Lags the supply voltage. Now the current drawn by the motor from the supply, that's the question. Current drawn by the motor from the supply lags the supply voltage, leads the supply voltage, in phase, or no load current is 0, like that you are asked. So you all know that magnetizing current, this is a common word you listen, magnetizing current. When you draw phasor diagram, this is V, this is IM, we generally write. If this current, which is lagging the voltage by 90 degree or 0 power factor lagging current, if you say magnetizing current, if this component is magnetizing, exactly the opposite component is demagnetizing. If a stator current is magnetizing, you have to say lagging component. If the stator current is demagnetizing, you have to say leading component. So this is leading. The current which leads the voltage is demagnetizing in nature. The current which lags the voltage is magnetizing in nature. Simply remember like that. So now in this case, when the current is demagnetizing, it should be taken as leading current. So answer is leads the supply voltage. So in this particular question, you will see a word called excitation losses. In the power stage, when I explained you previously, there is no excitation loss, I have not written. But how to interpret excitation loss, where to take it into consideration, I'll tell you now. So first, A 500 volt single phase synchronous motor gives a net output of 7.46 kilowatt and operates at 0.9 power factor lagging. RA 0.8. If iron and mechanical losses are 500 watts, excitation losses are 800 watts, estimate the armature current and the overall efficiency of the motor. Overall efficiency or simply efficiency or commercial efficiency, all are same. Overall, that word itself tells you how to consider everything now. So first, so in the question it is given iron and mechanical loss is 500 watts. So considering armature copper loss, iron plus mechanical loss or friction and windage loss, that combination, these are the total losses. In this loss, stray loss is not mentioned, you can ignore directly. Excitation losses are given but don't take. Why you should not take is in the power flow, in the power stage they won't come, because in the alternator and synchronous machine excitation system is separate. A separate excitation system is taking care of all those losses in the excitation system. You have to consider excitation losses while calculating the overall efficiency of the system. You have a particular output from the system, so in the input if you want to calculate efficiency overall, then only consider excitation loss, otherwise don't consider. Means for calculation of IA, if you consider these lines, there is no concept of excitation loss. That's what I want to differentiate here. So IA is calculated on the basis of armature copper loss and the iron and friction and windage losses. After calculating IA,
A 5 MVA 11 kV 50 Hz 4 pole star connected alternator with excess 0.7 per unit is connected to infinite bus. Find synchronizing power coefficient and corresponding torque coefficient per mechanical degree displacement of the rotor. So here I will give you formulas for electrical degree as well as for mechanical degree. First, you know synchronizing power coefficient synchronizing power coefficient is dP by d delta its units are watts per electrical radians. As you know, 1 radian is 180 by pi degrees. This can be again written as EV by XS cos delta into pi by 180 electrical radians converted into electrical degrees, watts per electrical degrees. If a question is asked per electrical degree, use this formula. If the question is asked per mechanical degree, again into P by 2. Now the units are per mechanical degree. Remember these three.
what is asked in the question is also important: per electrical radian, or per electrical degree, or per mechanical degree displacement. So when excess is given 0.7 per unit or 70 percentage, it should be taken like this. Excess is producing a drop, IA excess drop. So there is IA excess drop of 70%. That's the meaning. You know, per unit reactance or per unit resistance is representing per unit drop. So 70% of V. So 70% of V means 0.7 into V, IA excess is. From that we can find out excess. So first it is given in the question, no load. Find out the synchronizing power coefficient for no load condition. No load means E is equal to V, delta is equal to 0 you can take, and directly you can substitute. So once you know synchronizing power coefficient, it is easy to calculate synchronizing torque coefficient. All you have to do is multiply into 60 by 2 pi ns. So it is given 4-pole machine. So 1500 RPM is synchronous speed. Substitute 1500 and substitute the power here. You will get a number. So if you are asked for no load condition, this is the way. And now you are asked for full load 0.8 power factor lagging. For full load 0.8 power factor lagging means IA at an angle phi. So what is IA? 262.4 at an angle minus. Phi value is so when you know I at an angle phi and you know V, you have to calculate E for that. Then So hope you understood how to interpret these formulas accordingly for no load condition, for load condition. And now we see some questions on DC machines. A 500 volt 87.75 kilowatt 1500 rpm DC motor runs at rated load with efficiency 90%. The armature has 720 conductors and shunt field resistance is 100 ohms. Find the demagnetizing ampere turns per pole if the brushes are given a shift of 3 segments at rated load. Also, calculate the extra shunt field turns required to neutralize this demagnetization. You already know in theory, we find demagnetizing ampere turns per pole to find out the number of extra turns required to be placed on each pole to compensate or to balance this additional demagnetization happening due to the brush shifting process. So, it was given 3 segments. There is a brush shift of 3 segments. All you need to know is what is a theta, brush shift angle theta. So first you have to know each segment angle. If you want to know each segment angle, first of all you have to know how many segments are there on the commutator. If you want to know how many segments are there on the commutator, you should know how many coils are there on in the machine, because number of commutator segments are exactly equal to number of coils. That's the reason. So there are 720 conductors. As nothing is mentioned in the question, you can take directly single turn coils only. If the question contains there are 18 turn coils like that, it's a different story. If nothing is mentioned, you can directly take single turn coil. So 720 conductors means 360 turns. Imagine on the commutator there are 360 segments like this. Each segment will occupy 1 mechanical degree. That's the basic. So if there is a brush shift of 3 segments, means 3 mechanical degrees. Theta, brush shift angle theta is 3 mechanical degrees, or simply 3 degrees mechanical. You know how to convert mechanical into electrical because in the formula theta is electrical degree. So into P by 2. How many poles are given? It's 8 pole. Number of poles are missing, 8 pole. Data is missing, consider it is a 8 pole machine. As the question belongs to motor, as output is given to you, efficiency is given to you, calculate the input. Because the motor draw electrical input, that is V into IL. V into IL is this. From this you can calculate IL. Once you know IL, as you know ISH, we can calculate IA. So consider the data given 8 pole machine with wave winding. So number of parallel paths are 2. You know the formula, ATD by P is theta 2 theta by 180 into IA by A Z by 2P. This is demagnetizing zone, ampere turns per pole. Demagnetizing ampere turns per pole. Why IA by A means the current flowing in the turns is not IA by A, parallel paths. A is parallel paths. Per pole, that's why by P. Z by 2 turns. So once you know demagnetizing ampere turns are 570, if we want to find out turns, if you want turns from ampere turns divided by amperes, simple. The number of extra turns to be added on each pole into the current flowing in them should be equal to this for balancing the demagnetization. So from this NSH extra is equal to a 6-pole lap wound generator is running at 1200 rpm. Find the reactance voltage if the self inductance of each armature coil is 155 microhenries, armature current is 120 amperes, number of segments are 55 and width of the brush is 1.5 segment. Find the reactance voltage for linear commutation and sinusoidal commutation. The reactance voltage formula ER is EL di by dt concept only. L self 2 IA by A by TC. Di is 2 IA by A, from IA by A to IA by A, plus IA by A minus IA by A, 2 IA by A by TC. So what is TC means? Brush width minus mica width by V. What is V is peripheral velocity. Imagine segments per second. Peripheral velocity, how many segments are passing in a second. Because this is mentioned WB in terms of segments. See the question accordingly. WB is not given in centimeters or millimeters, it is given in segment wise. So segment by segment per second will finally comes out seconds, that is TC. That's the logic. So first, it was given the machine is running at 1200 RPM. When the machine is running at 1200 RPM, there are 55 segments on the commutator. When the machine is running or commutator is running at 1200 rotations per second per minute or 1200 by 60 rotations per second, how many segments pass in a second means 55 into. So there are 1100 segments per second. Therefore, TC will be substituting in the formula. Because it is lap winding, IA by A is equal to P is equal to 6. If it is asked for linear commutation, use this formula. If it is asked as non-linear commutation or sinusoidal commutation like that, multiply into 1.11. A long shunt compound generator has a shunt field winding of 1000 turns per pole and a series field winding of 4 turns per pole and resistance of 0.05 ohms. In order to obtain flat compound characteristic, it is necessary to increase the field current by 0.2 amperes. The full load armature current is 80 ampere. Calculate the diverter resistance connected across series field winding. It is given to increase the field current by 0.2 amperes. There are 1000 turns per pole already in the field winding. If you increase the field current by 0.2 amperes, which means ampere turns increment requirement is so the ampere turns extra required to maintain a flat compound character is this, which means series field ampere turns must exactly produce this only. Already mentioned, the series field winding contains 4 turns per pole. So, it is given IA is equal to 80. When IA is 80, into the field winding only 50 must flow. So, there should be some current diverting into the diverter. How much means 30? So, ISC into RSC is equal to ID into RT. You can say like that, parallel. So, ISC 50 into RSC value 0.05 by ID 30 is equal to RT, that is A 250 volt shunt motor takes a current of 41 ampere and runs at a speed 800 rpm on full load. Armature resistance is given, shunt field resistance is given. If a resistance of 2 ohms is placed in the series with armature, find speed at full load torque, speed at double the full load torque, and stalling torque to full load torque ratio. ISH is V by RSH, 1 ampere. Because this is a motor, IA is 40 amperes. So first, at a speed 800 rpm on full load, N2 by N1 is equal to EB2 by EB1 constant. Flux is constant. So this is initial condition. At full load, when the motor armature current is 40 ampere, when the speed is 800 rpm, N2 by 800 is equal to V minus when extra resistance of 2 ohms is added. That's the thing. Second case, speed at double the full load torque, T proportional to phi into Ia, as flux is constant, when torque is doubled, Ia also must be doubled. So 40 becomes 80. Same logic we have to do. N2 by 800 is equal to 250 minus 80 into So in the question, stalling torque. Stalling condition means n is equal to 0. You know, stalling condition actually by adding some extra resistance in series with the armature, you can make the voltage across the armature to come down and the speed will go down, and finally at zero speed, EB is 0, that is a stalling condition. When EB is 0, V is equal to IA into RA. Because you are adding some extra resistance, it is happening. So for stalling condition, IA is equal to V by RA plus R external. So this is the armature current for stalling condition. You know T proportional to phi into Ia, this is a shunt motor, T proportional to Ia. If you want to take the ratio of stalling torque to full load torque, obviously stalling current to full load current ratio you can take directly. So Ia stalling current. This is the stalling current. Full load current is 40. So So in this question, a 6-pole DC series motor contains 6 field coils in series. It is given that it is made into 2 groups in this way. So when you make into 2 groups, definitely the current drawn will be different, because to maintain the torque constant, as the flux has been changed, current also will change. So a new current will be drawn, IA by 2, IA by 2, new flux will be there, and what you are asked is what will be the speed for constant torque condition. So in this question I want to give you one conclusion which help you to solve other questions. First, T proportional to phi into IA, initial case IA1 square. Second case, T proportional to phi into IA, same logic. Here phi is proportional to IA by 2, means IA2 by 2. So in place of flux IA2 by 2, in place of IA2, IA2, so IA2 square by 2, because torque is given constant. Sometimes they will give you torque varies as square, or sometimes torque will be cube of the speed, like that. Any question, common thing what you can do is you can take one thing here, EB is approximately constant. If you take EB approximately constant, simply you can solve the question even without solving EB. But in this question I'll solve EB also to make you understand EB will be approximately same in these kind of questions. As torque is constant, you will get this equation finally, means the current drawn by the motor IA2 is 28.28 amperes. Here IA1 is 20 ampere. It is obvious, T proportional to phi into IA, when flux is reduced, IA will increase to maintain the torque constant. That's it. It's the first part of the question. Second part is, RSC is 1 ohm given, means the total resistance is 1 ohm. Now what happened is, this is 0.05, this is 0.05, because it is made into 2 parts, half of 0.1, 0.05, 0.05. So RSE2 is so EB2 is this is what I want to convey in this question. Normally what you know is n proportional to EB by phi, n2 by n1 is equal to EB2 by EB1 into phi 1 by phi 2. In this kind of questions where field weakening control kind of questions or flux is changing kind of questions, almost EB to EB1 ratio remains same. So even if data is given or not given in the questions, you can simply use like this, n2 by n1, phi 1 by phi 2, and you can get the answer. So n2 by n1 is 500, EB2 is 223.636 by 224 into phi 1 is proportional to 20 ampere, phi 2 is proportional to 28.28 by 2, because this is series machine, phi is proportional to IA, the current flowing in that winding. So 20 by 28.28 by 2. In this question, there is a diverter connected across series field winding. Then what will be the change in speed for same torque? That's the question. A 500-volt series motor has RA, RSC. It takes a current of 100 ampere at 600 rpm. Find the speed of the motor if a diverter of resistance 0.6 ohms is connected across the field winding while torque is maintained constant. Next, in this question it is mentioned again torque is constant, means T proportional to phi into Ia. Phi 1 Ia1 should be equal to phi 2 Ia2. And you know, in the first case phi 1 is proportional to Ia1, so Ia1 square is equal to phi 2 Ia2. Find the speed of the motor if a diverter of resistance 0.6 ohms is connected. So we have connected a diverter of 0.6 ohms. There is 0.3 ohm resistance in the field winding. So when the new current is I2, what we can say is ISC here is equal to I2 into 0.6 plus 0.3. This is 0.667 I2. Phi 2 ISC. I2 or IA2, both are same. IA2 or I2, anything. Phi 2 is proportional to ISC, current flowing in this particular winding. So ISC is I2 into this, so we'll get a number here. Phi 2 is proportional to ISC, this. T2 proportional to Phi 2 IA2, so substitute. You will get 0.667 IA2 square. This is T2. So now T1 is equal to T2. IA1 square is equal to 0.667 IA2 square. From this, IA2 is in the second case, this resistance is 0.3 parallel with 0.6 plus 0.4. 0.3 parallel with 0.6, that is this. When you connect a diverter across a series field winding, the current will divert. The new current flowing in this is ISC 0.667 I2. And how to find out I2? I2 or IA2? By equating the torque. Torque is constant. IA1 square is equal to this. From this you will get new value. Once you get IA2, you can calculate ISC, because this is the current who decides flux in the second case. Means in this form, phi 1 by phi 2 when you write, phi 2 is proportional to this current only. Phi 1 is proportional to 100 ampere. Phi 1 is proportional to 100 ampere, phi 2 proportional to this current ISC. So N2 by N1, EB2 by EB1, phi 1 by phi 2 concept. So EB2 you know how to calculate with new current. So dear students, I'll stop the session here. I wish you all the very best. Coming next week is very crucial. Solve as many questions as possible. Wishing you all the best. Thank you so much.